So I assume that you hear me well and you see my notebook here. So let's start. So chapter 27.1 or subchapter. And as you can see, the whole chapter will be about the Big Bang and thermodynamics. And first chapter is about time symmetry in dynamical evolution. And it says that like most of these successful theories in physics are actually theories of dynamics. And dynamics is basically the concept or model which tells us what world will be like by some initial data. So it's kind of equal or similar into approach to the partial differential equations, which model the situation in terms of like the future evolution. So you have some kind of the initial condition, you have some rule, some dynamical rule, some partial derivative equation, and you evolve with that, like building a trajectory basically, and predict how the system will evolve. Sorry, Marco, could you please mute because I hear you?
Sorry.
Yeah, thanks. Okay. So, and those successful theories actually been driving the thought that basically like the dynamics should be elegant. So our new theories should have elegant dynamics, and therefore, because those dynamics described using mathematics, like elegant mathematical description. And also Penrose tells us that there is a contrast to the dynamic approach. It's a static approach which tells us how world is instead of how world will be like. And he says that one of the example could be the Kepler laws, and those laws tells us what the world is like. But actually it also follows from the dynamics. So anyway, dynamics is at the root, and therefore we can kind of safely say that dynamics is at the heart of every successful theory in physics. And what's interesting is that physical laws are symmetric in time, and actually mathematics is good in there. Everything is fine with mathematics. In terms of physics, there are few exceptions, and Penrose connects them with quantum mechanics, and he says that actually our evolution, so that's like measurement stuff and those discontinuous wave function collapses, he says that there are some problems in there, and also there are some problems in general relativity connected with the black holes and space-time evolution, because like I think he been saying in there that space-time is kind of the like evolves dynamically together with the whole world or something. Like it's hard to separate space-time from everything. Let me see. Yeah, he says that the very structure of the space-time into which the evolution flows is part of the physical state to be determined. And that has some particular implications in the context of the black holes, as we will see later. So yeah, that's it. But the main question here is, if we combine that future evolution point of view, dynamical and PDE-like stuff, with the physical law symmetry in time, then we have a reasonable question, like why we don't evolve same equations into past. And that means why we don't specify a final condition and afterwards just evolve system back in time. And to answer that, we need like go more into something more thermodynamical. And we are coming to the subchapter 27.2 about submicroscopic ingredients. Any questions about the first one? Okay, then I will continue. So, and in here, Penrose starts with talking about...
Oh, sorry.
Yeah.
Yeah, I remember now. So the first one, it seems very much like determinism. Isn't that right? In that you, having one state of the system, you could predict all the following states.
Yeah, it seems that you are right. Yeah. And probably that's why we have some problems with measurements in here. So because I will have some kind of like non-deterministic looking way of evolution where you have that kind of randomness going on. But yeah, I think we will discuss that later in chapter 30 or 29. Yeah.
So one question.
Yeah.
So I was wondering, like the non-determinism and relativity, does it have something to do with that? It's not possible for us to observe beyond our light cone. So although it might be deterministic, but it's not possible for us to know all the beyond what we are confined by the light cone. So there will always be something that is undetermined to us.
Yeah. As Penrose said already in chapter 17, I think, he had been talking about that causal structure in space-time, right? Described by those conuses. I think that's the same thing you are talking about currently, Yuri, right?
Yes. So yeah.
Yeah, actually, question of determinism is pretty interesting one, but it seems that that's not the right time to discuss it because we will go too much into like to the side. Okay. Yeah, so let's continue with some microscopic ingredients. And at the beginning of that subchapter, Penrose talks about microscopic systems. And it means like systems like a gas with a lot of particles moving fast. And because of the nature of those systems, in the practice we use average like parameters like energy, temperature, I don't know, pressure, volume, something like that. And I don't know, he also have a mass and momenta here. Not sure about why those are average somehow. Yeah, like we cannot, yeah, got it. He just saying that because like if you have a lot of particles, it's hard to say what is the momentum of every particle. So you should talk in a more global sense, like what is the momentum of that cloud of a gas or something. Yeah, but anyway, for those microscopic systems, time reversal is still true. But as I have said already, because of the average like parameters used, or other way around actually. So because of the little knowledge we could have about separate particles, we have those average like parameters actually. And the question is, are those averages good enough to determine dynamics? To determine that, as Alex have said, deterministic evolution? And Penrose answers that the answer is actually yes, but only in the good enough systems, because there is a special subclass called chaotic systems. And those are the systems which are critically dependent on the initial value. They are also described by the PDEs, but still, even really small discrepancy or like change of the initial value will produce an unpredictable and really different result of the evolution. Yeah, and here, let me see if I have any paper.
Think butterfly effect, I think.
Yeah, that's like butterfly effect. I think it's called stability or something like that in differential equation theory. That basically, if you change your initial, for example, you have some kind of at time t0, you have value something like x0 here. And if you have that value, you can kind of find your solution in time using your dynamics. And it'd be, for example, like this. And stability means that if you will take, for example, x0 plus some small epsilon here, then your new solution will be in a small interval from the previous one. So basically all solutions are continuously dependent on the initial condition. And that's called stability for the differential equations. But those chaotic systems are not stable actually, or maybe quasi-stable, I don't know the right mathematical definition, but the basic idea is even for small discrepancies in the initial condition, you may have the same trajectory here, but at some point of time, it will be reclined really much, and evolution will not be at all similar to that evolution here, for example, and the path will just go away really wide. So that's like the idea between chaotic systems as kind of unstable, and if you change initial value, they will produce really different solution for your equation. And the interesting thing is that those chaotical systems, I just want to make a small reflection on those, because I think that that theme is really important. I actually I heard about them a lot in my university, but first time I really got into those was when I've been watching, I think those were Stanford lectures by Robert Sapolsky about behavior of humans, or something like psychopathology, I don't know, and physiology. So a lot of different stuff were included, like your brain, hormones, genetics, etc. So basically, it's kind of like a course in biology. But it was really interesting that he recommended to every student in there this book written by James Gleick called Chaos. And actually, I recommend it for reading. I even can send you PDF if you want. That book is really interesting because it describes like the history of the chaotical systems, like about those weather effects, butterfly effect, and other stuff. But what's interesting is that it's interesting how to describe those systems in physics, and can we have a nice theory, like physical theory of those chaotic systems, because like even really simple examples could be chaotic. So Penrose in his book, he shows that pendulum with magnets on a board, so even such a simple system with a pendulum here and 4 magnets will be chaotic, and it's kind of hard to predict to which magnet at the end it will be like rested or like attracted to at the end. So yeah, and I also like an example from this book that, for example, if you have, how does it call? How is it called? Like if you have a swinging sphinx, probably that's the right name. Like if you have a piece of wood and ropes attached to a tree and you just swing on those, how is it called? Like swingers? Probably that's not the right word. Did you understand what I'm talking about? Yeah.
Take a swing.
Like a swing, yeah. So you just swing on it, like a baby swings on those stuff, right? So if you just swing a baby like a pendulum, well, probably the right example also is just a pendulum. So like pendulum.
Or double pendulum, even better.
Yeah, double pendulum is also a nice example, but even a one based pendulum with that one stick in here, it could be made a chaotic system by just applying a small engine or small push to it. So if you will try to give it a small push and help it to bounce basically and swing, then you will make it chaotic system. So yeah, probably I just been reading that book a long time ago, and I don't remember that example, but I remember that emotionally I was like in awe while reading that. So like yeah, main thought from everything said about that, try that book. Yeah, and also one more thought is that like it was an interesting fact that biologists or like neurologist like Sapolsky is interested in mathematics and is interested exactly for the chaotical systems. And he said that if he was gifted at math, he'd been trying to understand chaos because he feels that like the secrets of life and secrets of biology are in the chaotical systems, because in the chaotical systems you can see fractals in here. They have something what's called emergence or emergent. They could be, probably it's better to say that they could have an emergent behavior or something. And they encode the complex information
With simple rules.
Yeah, with simple rules. Yeah, thanks. So effectively is the right word. And so those fractals and chaotical systems are kind of connected, and a lot of chaotical systems and complex systems with the emergent behavior, they possess that fractal nature. So like trees, for example, right? And also the veins in our body and a lot of stuff. So, and he says that even doctors and medical stuff could benefit from chaos actually, because if you think about your organism as a fractal, you maybe can produce some kind of more effective medicines or something. So it's really interesting theme, and I encourage you to take a look at chaotical systems a bit and how they could be connected with life physics. I think it's really a fascinating area to like for research. Okay, so sorry for such a long side talk, but I think that was really important.
I have one thing to add about chaotic systems.
Yeah.
When I think of like how to determine whether a system is chaotic, if you have to look at the phase space orbits. So you had just shown like a sort of position versus time, or like state versus time sort of thing. But if you look at like a position versus momentum graph for like a non-chaotic system, yeah. So let's do momentum on the vertical axis, yeah. And so, like, you could imagine if you like drop a ball. Well, if you just like drop a ball and you're on Earth, like you can, the position will continue growing, and the momentum will continue growing as well. It'll just like, if you drop it from some initial height, then it'll basically like fall down. So this is I think what we're looking at here is a closed orbit, right? This would be like a pendulum.
Yeah. But like our bouncing ball, right? If there are no like frictions and.
Right. Yeah, it could be a bouncing ball. So I guess, like if you started by like throwing the ball like downward, you gave it some initial momentum, you would displace this circle, right? You would shift it upward. But also if you threw it from a higher place, you would displace the circle just to the right. Do you see what I'm saying? Like if you change the initial conditions, you're like moving where this circle is. So the way to think about chaos is that when you move this, when you change the initial conditions, the shape of the orbit actually changes. So for this pendulum system, you're just displacing the circle, like either up or to the right or left, but it still remains a circle. Whereas for a chaotic system, what happens is these orbits will actually like fold over on each other. So you can imagine like the circle flattens out into a pancake and then folds over on itself. And that actually ends up happening repeatedly.
Yeah, but am I right that if you change like the initial condition for a pendulum, you will have like a bigger circle or something?
Right.
So you will have some kind of like concentric circles here for different initial values.
That's right. Yeah. So I'm thinking of like a particular circumstance where like the ball does not bounce back up or something. Like if you just drop it, the momentum continues increasing, and the position is decreasing, and it follows like a parabola. And so you could imagine. Maybe I'll draw it, and I'll send an image in the chat.
And if the circle remains the same size, that means we have no entropy, I guess.
Well, the size of the circle is related to the energy of the system, as Slav was pointing out here. It gets bigger if we have a higher momentum in the beginning.
Yeah, so like the bigger the amplitude, the bigger the momentum.
Yeah, but it would be shrinking dynamically because of entropy in a life system, basically.
Yeah. So something like that. Yeah. So you will lose energy, like because you will lose energy and it will be converted to heat of the air molecules. Yeah.
Exactly.
Yuri, have you been saying something?
Just it's a different comment. So I just wanted to comment that chaotic systems are different than stochastic systems. In our everyday life, actually, we see a lot of systems that are stochastic, but nonetheless stable, unlike chaotic systems. Whereas chaotic systems are still deterministic.
That's an important distinction. Is that at any point in the evolution, if you can really well measure the state of a system, if it's chaotic, you can actually predict the next value. But if it's stochastic, you can't, even if you know the state very well.
Yes, so I'm seeing the picture. And what we have here, Joe?
So I'm just imagining like, imagine you're like at the top of a staircase or something like that, and you drop a ball. That would be a case in which, you start from the origin in this top graph. And basically momentum increases, and position increases, like basically the amount that it falls increases, right? And if you throw it down, then the position increases faster or whatever, right? I drew 3 paths here that represent different initial conditions.
Mhm.
So in the one at the origin is basically you just like let it go at the top of the stairs, and then the one on the x-axis is like if you take a couple steps down the stairs before you drop it. And then the one on the like vertical axis is if you're at the top of the stairs and you throw the ball down. So you could see like basically the shape of this evolution is the same for both, or for all these situations.
Mm-hmm.
But you know, the initial conditions really kind of are distinct. You can tell, like from a specific point here, you can tell where you started from. Like, I mean, an intuitive way to see this is like, if you were at the bottom of the staircase and you were watching that ball fall, you could tell whether we're going faster or slower, right? So you can tell that.
Yeah. So it's like
down or just up.
it's actually determinism, as Alex mentioned, right?
Right, and so this second plot that I've drawn, I don't have as good of a like physical intuition for this second system, but I just wanted to show the idea. It's like, given 3 of the same starting points, the evolution starts like overlapping. They become very close, even though there are like different initial conditions. If you tried to measure the state of the system toward the end of these lines that I drew, you would have a very difficult time resolving which initial condition produced that state of the system. See how they like kind of fold in on each other? That's this is one way that I characterize chaos. Is like a variety of initial conditions will end up eventually producing the same behavior. And so this is kind of turning it on its head, right? Usually people say, given an initial condition and a change in an initial condition, they vary quite a bit. But it's actually the same thing to say, like, if you measure the state of a system, it points to a variety of initial conditions.
Yeah, I just sent like a picture of the most famous what is called attractor.
Yes, Lorenz.
Yeah.
So yeah, you could see like all these orbits. They're very close together, and so if you were to try to measure the state of a system, there's a variety of initial conditions that would actually get you there.
Mm-hmm.
So that's sort of what I was trying to draw with the second plot there.
Yeah.
And I think it's an interesting way to characterize chaos, because it's not like, usually they talk about it as varying the initial conditions, but when we interact with chaotic systems in the world, you measure the system and you try to estimate the initial conditions.
Yeah, I remember something probably a bit vague about that attractor, that like it's almost unpredictable, like when the system will switch from one orbit in that attractor to another one. So the mystery is in that bridge between those two orbits or something. So in between them, probably where those evolutionary lines are too dense, as you've been saying.
Right, and when you measure something, because there's an uncertainty on your measurement, you can imagine, like, rather than your measurement corresponding to a point in this space, it's like a tiny circle or something, and that circle encloses quite a few orbits.
Mm-hmm.
So all of the orbits that are enclosed within that circle are the possible initial conditions that would get you to this state.
Yeah. I also recalled about one interesting course course, right? Like a playlist basically of videos on YouTube from an interesting guy from Belgium. He created he'd been creating visualization for mathematics when it wasn't so popular. So one of the probably first visualizers of mathematics on the internet, actually. And he also has an interesting playlist about like imagining 4D space or something, and also we have used his videos when we've been talking about the fiber bundles and the Hopf bundle also. But anyway, he has also interesting playlist about chaotical systems and like modern theorems in those, and everything is visualized in there on 3D models, like pool tables and etc., pendulums, those trajectories, phase spaces, and a lot of theorems about chaotical systems in there. I will send a link after the call. Okay, so should we continue?
Yes.
Okay. So we stopped at the chaotic systems. Let me see. Yeah, and in terms of the time reversal, there is a problem with those chaotical systems. Probably we have settled that already, that we have what is called like retrodiction failure. So we, by taking a look at the final state, we cannot say how we come to it from what exactly like initial condition. And Penrose connects that somehow with the second law of thermodynamics. Let me see how exactly.
Well, wasn't it this about, like you read on the heat flows from hot to cold? So we can see if we have a state with difference in hot and cold areas where it's going to flow. But once it's reached equilibrium,
Yeah,
we cannot tell from that state the direction.
Yeah, thank you. Yeah, that's it. Yeah, so actually it is connected by that argument that heat flows from hot to cold, and if we will apply that to the same thing to that example with hot and cold air, then retrodiction is hopeless, because we cannot say like how to separate basically a bunch of the hot air molecules from the cold molecules or something. So it's really undoable. And he says that
on average that would be, if we could trace every molecule in a classic system, then we could retrace it. Isn't there like a Maxwell's demon example of this? Yeah, maybe I can make something about it.
Yeah, I heard something about Maxwell demon, but I don't remember exactly what is that. But
Maxwell's demon.
Yuri?
The Maxwell demon is the thing about reversal of second law, that you imagine that you the familiar example that I know of is that you imagine that you have a box of ideal gas and you have in equilibrium, and there is a partition between the little door, and the Maxwell's demon sits on the door and measures he knows the incoming particle, the velocity of the particle, and if the particle is a bit hotter, then it opens the door and lets the particle into one compartment, and if it's colder, it keeps it in its original in one compartment. And as time goes on, this system will naturally become the reversal of it will become hotter in one side and colder on the other side.
So it will separate air into two portions, right? Like in a hotter one and the cooler one.
Yeah, and that's the reversal of the second law of thermodynamics. And it was argued that this opening and closing of the door does not cause energy, and therefore if you so the Maxwell's demonism was originally invented as a way of destroying the second law of thermodynamics.
But it failed, it seems, right?
But the reason is strange to me. So the reason now that people think is that because information costs energy. So you can't so the information itself costs energy, and if you take that into consideration of the whole system, then Maxwell's demon, the system actually follows the second law of thermodynamics. So, yeah.
Yeah, interesting. Okay, so yeah, and therefore you can make a conclusion. If retrodiction is hopeless here, then physics is mostly concerned with predictions. And Penrose said that actually second law is essential here. So because of the second law, physics are more concerned with prediction than retrodiction. And some people have doubts about the second law because they could say that it is vague or imprecise, and maybe that it can't compare with precise dynamical laws of physics, like conservation of energy or superposition principle. But Penrose says it will show a mind-blowing precision hiding behind it later. Yeah, and we are coming to 27.3, subchapter about entropy here, where at the beginning Penrose introduces the first law of thermodynamics, and he says that he gives us an example. If we throw a ball or a stone, then eventually it will stop because of the air resistance, and it happens because kinetic energy converts to the heating of the air and the body itself. And yeah, he also says, like the note here, that heat and temperature in thermodynamics are actually statistical values, some kind of averages, as we have said already. And he says that conversion, like kinetic to heating, has to do with the what's called like the first law of the thermodynamics, which is actually equal to the statement that energy is conserved in the isolated system. And it's kind of equality-like law. But second law of thermodynamics is about actually inequality instead. And it says that entropy rises with time. And entropy could be understood simply as randomness, that randomness in our system will grow in time. Yeah, and to understand that concept better, what is entropy, we are coming to what is called Boltzmann definition. And to get it, first of all, we need to consider a phase space plus boxes inside of it. Those boxes on the phase space, or like subdivision of the phase space into boxes, is called coarse graining. And those coarse-grained boxes are corresponding or equal to the macrostates, actually. And macrostates, it means that every point in the phase space in that box will correspond to some kind of undistinguishable for the current observer macrostate. But there is a nice question here, like where to put the boundaries of the boxes, because we can be more precise, have more precise tools, take a look deeper and deeper. So maybe coarse graining will be like coarser or grainier. Yeah, and it seems that it depends on how closely do we look at the system. But anyway, Boltzmann formula actually was originally defined by logarithm without that k, I think. And only after Planck introduced his units that K Boltzmann constant was introduced. But anyway, we have that formula for entropy. Entropy S equals to K, where K is Boltzmann constant, multiplied by the logarithm of the volume of the box V here in the phase space where basically our point is, where our system is, or to which this current state of the system corresponds. Yeah, so that's like the basic idea behind the Boltzmann definition, that entropy could be measured by taking a logarithm of the volume of a microstate in a phase space. Yeah, afterwards Penrose says that this definition is actually subjective, but it is very useful. Subjective because of those coarse graining questions. It's not absolute, non-absolute, of course, because we can make different those like box subdivisions. But anyway, it's useful and it's non-fundamental also. It seems kind of hacky and a bit maybe superficial, but it's convenient. So the main conclusion here that this formula is probably the best way we can make sense of the entropy, basically. Yeah, and he says that actually logarithm plus really big ratios between volumes, which is the same as a little difference where to draw lines. Yeah, so we have really big ratios between different volumes, and that means that if we will not be really precise with our coarse graining, it doesn't matter much. And also logarithm helps us because it gives us also more coarse graining arbitrariness. So we can be a little messy with the subdivision of the phase space here. Yeah, and afterwards Penrose asked about like maybe we could have a more fundamental notion of entropy, and he says that we could have the answer if we will consider black holes, or we will take a look at the quantum mechanics, but we will take a look at those questions later. Yeah, and to grasp that notion a little bit fuller, we need to take a look at 27.4, where he talks about Boltzmann entropy and gives us the first example. And in that example, we have a gas container where we have like that cylindrical container C and that spherical R connected with a small bridge here. And R is roughly C over 10 in terms of volume. And the goal is to find entropy for the gas to be entirely in R. So basically, it's kind of the measure, it's kind of like it's like a probability. So let's see. He says that we will use instead using the polyfermi statistics. We will use Boltzmann statistics, which means that all gas molecules are in principle distinguishable. So we will not talk about fermions and bosons here. Just let's think about those as balls, and that's it. And we have 1 liter of gas inside that 1 liter container. And it means that number of molecules is roughly 10 to power of 22 here. And that means that the ratio of the volumes in the phase space for the container R versus container C here, and it means like that all gas is inside R versus all gas is inside like the whole container. I think that C probably is the whole container, like cylindrical plus R also. And he says that that ratio will be 10 to minus m, and you can see that m is really large number here. So we will have a really tiny ratio here. Yeah, and that means that we will have a really small probability for a system being in the state where all gas concentrated in R somehow. And the difference in entropy, he just finds it, I think, by taking a logarithm of that 10 to minus 10 to power 22, basically. Yeah, and he, by multiplying it with the Boltzmann constant, he gains that 0.3 joules divided by Kelvin here. And he says that almost all of these is he says that almost all of this is volume. Yeah, sorry, one moment, need to check up what does it mean.
I'll take the moment to
Yeah, please.
mention something about heat flowing from hot to cold areas. There is an exception to this. So there's an interesting footnote about this. He writes, this assumes that the specific heats are positive, which is normally the case, but with black holes, this assumption is usually untrue. So I assume we can have negative heats with black holes, and the flow would be reversed.
Yeah, I heard about something like QFT effects and black holes. Like if you have creation annihilation pair of particles near the black hole horizon, and one particle will be like being eaten basically by the black hole, and other one will fly away into the space or something. So they will have some kind of radiation going on in there.
Yeah, Hawking radiation.
Yeah, so what that meant is that almost all of the entropy actually described by that equation is the entropy of VC. Yeah, so maybe that's not right to say that it's a difference.
What was C referring to?
C is like the whole container. So basically it means that the volume of the phase space, which corresponds for the system where gas is distributed equally over the whole container C, with R together basically, so C and R, then VC will be a lot more bigger in the volume. So we are coming to the thermal equilibrium question here actually. So it will be like thermal equilibrium point or box for a system, and the volume of it will be much bigger than all other volumes. So VR will be like a small box at the border here, and therefore like almost all of entropy will be concerned with the thermal equilibrium box and not with VR. That's basically the meaning of it. So I'm not sure about that formula. I don't know if that's much entropy or not. Probably not, and probably actually it means that like that change in entropy is really small, and it is small because almost all of entropy is inside that VC volume, and therefore it will almost like not change. Will not change.
It will with most certainty fill the entire container rather than just be confined to this.
Yeah, so
subspace.
Like because those logarithms they are measuring some kind of like probability here, and like usually if you work in probability theory, those ratios of volumes will tell you a probability of a system being in that state, right? So we have a really small probability here, but by taking the logarithm of the ratios, you will have a difference of entropies. Yeah, and that logarithm will be really small. And that basically means that the most probable situation is that system is inside thermal equilibrium or VC box here. Okay, and afterwards Penrose tells us that in practice we'll have a non-ideal situation where we will have 99% of gas in R, but that won't change the situation because of the coarse graining insensitivity, as we have talked about previously. And also one more note that logarithm makes big numbers manageable, plus makes entropy additive. So if you will combine systems, then phase spaces will be producted or multiplied, and entropies instead they will be added. Yeah, and that's the right time to talk about thermal equilibrium. And thermal equilibrium is like the biggest box which exists in the coarse graining with a far exceeding volume, and phase space will look something like this, and basically whole volume of the phase space will be almost equal to the thermal equilibrium box. So that's kind of really big box. Okay, and from that thermal equilibrium follows the Maxwell distribution for velocities, which is actually half of the Gaussian-like distribution. Okay, and the thermal equilibrium situation has the biggest entropy, and that equal that eventually system will be there. So with the really big probability, if you will give system enough time to dissipate, like to lose energy or something, or to convert that energy to heat, system will get into that box. Okay, and also he says that there are also other systems in which like Maxwell distribution do not work. Let me see exactly how Maxwell distribution appeared here. Yeah, he says that if we think about gas to be made up of identical spherical symmetrical balls in thermal equilibrium, then the distribution of velocities takes up the Maxwell distribution. So in thermal equilibrium, in the case we will think about the particles as like similar balls, we will have just regular Gaussian or normal law. But if there will be some kind of like more elaborate theories where those molecules will be sort of different balls of different nature, I don't know. So in more complex theories, Maxwell distribution will not work. But anyway, will work what is called the principle of the equipartition of energy, which means that energy distributes equally between different degrees of freedom. Okay, yeah, and yeah, we can also ask the question like what we should do or use before we get to the thermal equilibrium for the evolution which happens before. And Penrose says that there is what's called Boltzmann equation, and it's used for those situations. And at the end of this subchapter, he also talks about macro objects behavior with a lot of micro points or particles. And he says that maybe you could guess that there is a whole science talking about those, which is called statistical mechanics, actually. Yeah, so if you want to study those macro definitions for physical systems, statistical mechanics is the right place to look at. Okay, subchapter 5. Any questions? Maybe you have any questions? Okay, let's continue. Probably I will turn on lights. Okay, so 27.5 is called derivation of the second law or not, and it starts from like the situation where we have a phase space and we are trying to init system at some state. So just take a point in a phase space and let's try and move it with some kind of dynamics. It doesn't mean matter what kind of, actually, because we want to like probabilistically tell what will happen with system if we will not be concerned what form of the dynamics do we have in there. And from the form our phase space takes, we can say that it will move into larger and larger boxes in P. And that means that even if we move the point randomly, we'll have like most basically like the probabilities of getting into the different microstates will be proportional to the volumes of the coarse graining boxes, and therefore we will go into larger and larger boxes in the dynamics, and that will correspond to the increase in the entropy. And that means that we have like our second law of thermodynamics. Yeah, and that also means that we will have a very low probability to get into smaller box. The picture here is like that. So we have that situation at now, and we move that pen randomly or something, and you could see that we are getting into bigger and bigger box. And even if you move the evolution something like there, you will still get into the bigger box, bigger box, bigger box. So it just happens that like coarse graining is done into that such way that you always will encounter bigger and bigger boxes. I think that Penrose also kind of drawn it this way, so it's kind of tricky way. You can ask a question, why didn't he put a really small box here, for example, so we can encounter it randomly here? Probably we can, actually, but as he says, the probability of it will be really small because the volume of the neighboring box or exterior box here is much larger. So maybe that's the reason why he didn't draw any small boxes in there. But anyway, that small box will kind of break the second law. So maybe he just wanted to make a point with his example and didn't want to go to the side talks. Okay, so, and this derivation, it looks really easy. It do not depend on dynamics details. It's kind of obvious, but is it fundamental or not? And actually, he also includes Eddington, Sir Arthur Eddington quote here that, like, if you, if your theory is found to be against the second law of thermodynamics, I can offer you no hope, he says. There is nothing for it but to collapse in deepest humiliation. So, like, it just meant so that this example is kind of obvious, and it seemed really obvious for the people from the past. Okay, and yeah, but this implies strange conclusion that time asymmetry, we have some kind of time asymmetry in the symmetrical physics, in symmetrical laws of physics. And Penrose said, let's try and apply same argument to the past. And what we will see? And we will see the same situation, that entropy rises. Because if you will move or just like take and like you will try to move your evolution backwards in time, but in the same phase space, it will also go to the bigger and bigger boxes. So it doesn't matter for that example, like how you move to the bigger box. I mean, we only fix that one point now, and that's it. And if you will be able to deliberately put your evolution into the past, it will went the same way as it runs into the future. And that kind of defines contradicts the second law of thermodynamics, because we should see fall of entropy, but we see rise. And in the terms of our previous example is the container, it means that gas concentrates spontaneously in R. Probably because if entropy rises in the past, then in the future it will fall, right? And therefore the gas will concentrate spontaneously in R. That's what he's saying here. So if it rises into the past, in the future it will fall. And we could have those strange conclusions or examples in real life, but we don't have those. So, and he asked the question like how to prepare gas in R actually. And he says that to fill, we are, in practice, we are usually filling the whole container, then we close valve, and afterwards we pump air from C, and by C I mean that cylindrical, in that case only cylindrical part. So we are closing that valve here at the bridge, and we are pumping air from that cylinder. And afterwards we have like a vacuum in C and gas in R, so the system is prepared. Okay, but what we have used here, we used human basically and his force, and we therefore need to include experimenter into our system. And if we will include experimenter, we need to include food, we need to include sun, and and therefore we will need much bigger phase space. And second law is satisfied in that small example, but he says that even for such a bigger phase space where everything is included, we will still have the same problem with the past evolution. He also mentions an interesting concept at the end of that subchapter about flow of entropy, that basically like sun supplies us with low entropy photons or something, and it provides us like with air and food, and humans after eat those, use those, and afterwards can do the useful work. But I think that we will talk at the 27.6 more about that. Yeah, so we come to the question like how to talk about the universe actually, because we need to include sun, food, and maybe other planetary things and stuff into concern. And the usual way it's done in physics is actually by designating like the isolated and open systems. And Penrose thinks, first of all, that is a provisional explanation, because we need to look at the universe as a whole, and therefore we will still need like the need of the bigger phase space, which will describe the whole universe, which is called PU here. And the power of that isolated and open argument is in the possibility of an input from the outside to reduce entropy. So the same way we have seen that human can make an input, pump air from C, and therefore decrease an entropy. So it seems like a hack here. So like for smaller systems, by like closing our eyes and believing that system is closed or isolated, right? We can say that everything is fine. Okay, that's not a problem. But if you will have that experimenter pumping out the air, that system is actually open, and that will make things worse, and you will kind of have that effect where you will need to include into your system more and more and more stuff, and you will come to that PU space actually, and you will need your universe to be described by it. Also, Penrose talks about that it doesn't matter if our universe is finite or infinite, so we still will be able to describe it using some kind of a phase space. Maybe infinite dimensional, of course, but still. Yeah, I have a note here. A note says that, strictly speaking, we need to use cosmology plus general relativity here, but it is okay to skip those as for now. Okay, and afterwards Penrose does similar trick. He uses some point x of that really grandiose phase space PU, and that equals to the descriptions of all material content in the universe plus fields, so it includes gravity, electromagnetism, etc. And it means that we will have some kind of infinite dimensional space because of the fields, and therefore infinite volumes for our coarse-grained boxes. So what should we do in that case if our boxes are infinite? Penrose says that maybe we should use some kind of renormalization tricks from QFT or something. But actually, I guess he says that we shouldn't worry about that anyway. So it's a tricky, like, we should worry about that strictly speaking, but currently we can skip that question. Yeah, and one more note here, that general relativity doesn't have a preferable time t, but standard cosmological models possess that time. That's interesting note, and we will talk about the cosmological models later, so it's interesting how Penrose will explain that. Yeah, and also he makes a point that a lot of people in the physics community thinks that expansion of universe equals to the entropy increase. So there is some kind of connection between those two processes. But Penrose says that it is a misconception, it's wrong, and because the expansion of the universe puts into play what is called entropy sailing concept, puts some kind of the maximum of the entropy which entropy value which our universe could have, and it is wrong because he says because actually our phase space describes everything. It even describes different universes, so we cannot use that sailing concept, and it's not correct for us. Yeah. So he says that it will describe all universes and their expansions also. And that entropy sailing concept also will have some problems with the black holes theory and universe collapse. It means that if we have the expansion of the universe, and we could have also universe collapsing in some point of time, and I think it was somewhere in the Dr. Nobody film, actually. Yeah, but anyway, that universe collapsing will make the entropy lower and lower or something. So there's some kind of contradiction. It's kind of a vague point, but we should also know about that, the existence of it. Okay, one small note here says that usual second law picture is obtained in PU now. So basically he repeats the same stuff. He just says that we have that coarse graining inside. We can now experiment more and more with that PU space and go to larger and larger boxes. And to obtain finite volumes, we need to have finite universe or finite bounds on the available energy. And he says that one of three cosmological models satisfy that. But we can also allow infinite values and compare infinities, as we have seen in the chapter 16. And as we know, in mathematics, we have like cardinal numbers and ordinals or something. So we have different degrees of infinities, and we can compare the infinities actually. So maybe infinities are not a really big problem if we can compare those somehow. Yeah, and here we comes to the 27.7 and the Big Bang actually. Okay, so the 27.7 subchapter starts actually with a picture, and I will come to it soon. But what we have there, we have some kind of a path, like evolution path in the phase system. It's the same as the evolution of that system. And we have that path, and we're trying to randomly throw it into the phase space PU. And in the result, we will have three different possible variants of it landing onto the phase space. First one is random positioning. So it will fall randomly. And in that case, almost all of the evolution will definitely go into the thermal equilibrium box. And therefore, we will have no increase of the entropy, because we are in the thermal equilibrium and like nothing changes there with the evolution of system. It's the same macro state, and that's it. And that's not what we're seeing currently. So we are seeing that only like in a I don't know, thermal death of the universe, but universe kind of have that growing entropy right now. So to mitigate that problem, we can try and fix null point at some t0, t greater than 0. And now we will have the same problem we have had in the previous subchapter, where the entropy will increase as well in future and as well in the past. So we could think more a little bit and now say that probably for our system at the beginning of the time, where the time started, like where t equals 0, our system was at really small box B. And that way we are obtaining our second law. And it means actually that we will grow, like as system evolve, we will go to the larger and larger boxes. And it will happen because in the past we walked to smaller and smaller boxes. And there is a note here that if our path is going to reach B in the past, it just has to go to smaller boxes. So there is no kind of like a fixation of the dynamics in there. There is no bias in there for the dynamics. It just happens so that the box B is like have so much neighbors which are small boxes that our evolution just don't have any other choices as to go to smaller boxes. And therefore that makes the trick with fixing one end enough to deduce second law basically and make kind of interesting toy model with the phase space. And actually that B box is corresponding to the Big Bang region in the phase space. So, and on the picture it looks like that. So you can see at the picture A here, randomly thrown evolution is almost all inside the thermal equilibrium box, outer box here. And BC corresponds to fixing only null point, and you can see that if you evolve into future, you go to larger and larger boxes, and if you evolve it into the past, you will go to larger and larger boxes with a bigger probabilities and to that smaller region. So in theory, you can go to the smaller region, right? But the probability of it will be really small. So it's like not, it's just not probable. Okay, and for the last approach, you can see trajectory BD here, and BD goes to that smaller region because we have fixed our system at the time 0 in that really small box B here. Okay, so, and afterwards Penrose talks about historical reasons to believe into the Big Bang, in the Big Bang. And first of all, he talks about Friedman's research made in 1922. It was connected with the Einstein equation, actually. And also he mentions Hubble research made in 1929, where he discovered like redshift effect. And it means that the distant galaxies are receding. So we are obtaining explosion-like picture of our universe, where everything like kind of falls apart and moves on, therefore it means like that redshift means that spectral lines which we are observing for those distant galaxies have Doppler effect, and therefore they become like longer and longer and shift into the like more red spectrum. So visually it's like going for the galaxy from like a blue light to the red light. Yeah, and that means that galaxies moves with a speed from us. Yeah. Okay, and he also says that there were some theoretical predictions from Gamow in 1946, and also Dicke independently made some in 1964, plus at the practice Arno Penzias and Wilson in 1965, they were testing some kind of like really big radio telescope or something. And I heard that story, and it was kind of funny because they had some kind of strange noise. So they built a really big radio telescope or something, and they had some low noise, and they been thinking, what is that? Maybe that the noise is coming from leaves. And they cleaned up everything on from the leaves. Afterwards, they thought maybe it's some kind of like bird shit or something, and they cleaned it from every intruder pigeon or something, you know. So they made that really clean telescope, but that didn't help. So they discovered what is called like cosmic microwave background radiation, which is really uniform to 10 to the power of -5, and it's kind of have really low temperature, like 2.7 kelvins, and is associated actually with the Big Bang flash still coming to us, and it is enormously redshifted and therefore cooled, so that's why its temperature is so low. And that uniformity of the radiation which we are measuring nowadays actually is equal to the statement that early universe at the beginning of times was really uniform. Okay, so, and afterwards he discussed Sun and Earth and says that our survival is actually is not crucially dependent on the sun energy itself, and it is a misconception, or maybe not the right way to say it. What is useful actually is that sun is a hot spot in a cold space, and that is useful because if everything was hot, we couldn't have an ability to like extract the energy from the system. Yeah, and he says that actually energy received by the Earth is equal or roughly equal to the energy emitted by it. So, and it means received by the day and emitted during the night. So day-night cycles in terms of energy are kind of equal actually. And from the sun, we have high energy input photons, and from the Earth, we have the low energy output photons. And that means that actually number of those low energy photons will be greater than number of the higher energy photons. And that's actually equal to the entropy increase. So we have like much bigger randomness in here because we have much more photons outcoming from the Earth at night than the number of the photons incoming from the sun at day. Yeah, and how that happens actually, it happens by the same chain of the entropy we have seen, like flow of entropy we have seen here, with like really small and simple one about sun, air, food, and humans and work. But we can now enter a bit more details about that we have some kind of low entropy input, those low entropy photons flying into the plants, and plants use photosynthesis, providing us with oxygen, and also plants are food for the animals, so they are living by those photons from the sun. Animals live on plants, we live on animals and plants also, we breathe in the oxygen they produce also, and afterwards we make some higher entropy output to the nature. And we have figure 27.9 here. It's a beautiful picture by Penrose. You can see those more energetic photons coming from sun energy, plants and animals, and human eating. And at the night we have those low energy photons flying back into the space. So you can safely say, as Woody Allen mentioned that into the Love and Death film, that nature is kind of just a big restaurant and that's it. So we're eating something and that something eating something. So that's all the chain of the making low entropy input and producing higher entropy output. That's kind of it. Okay, so, and at the end of that subchapter, he says that actually gravity will play an interesting role in our discussion, and that's because star actually is forming up from the uniform gas using the gravity. So gravity kind of collapses gas into a star, and star afterwards provides gets low entropy from uniformness of gas. Let me think why that's and probably that's like it seems not so obvious why low entropy here, but Penrose says that we should think, or actually gravity is the other way around than entropy. So clumping in terms of gravity gives us higher entropy, and uniformity gives us lower entropy. So let's see the picture here. So you can see that over the time, if you put the gas into a chamber, entropy increases, and while it increases, the gas flows uniformly, and like flows through the chamber and uniformly fills it up. But if you add the gravity, then you will see that increasing in entropy, or like I think Penrose here means that like time arrow means entropy increase, and if we will take a look at the gravitating bodies, then we will see that using gravity those will clamp, and that means that in gravity situation low entropy stuff is connected with the uniformness, and high entropy stuff is connected with clumped things. So like the maximum entropy stuff is actually black holes or something. That's kind of interesting how he will use it later, we will see, but that's kind of the point he makes here, that gravitational system have a little bit different notion for the entropy here because of the gravitational clumping, and therefore I think he said that star inherits the low entropy from the uniformness of gas. So gas had low entropy, and yeah, it just somehow not obvious because stars have like bigger entropy, right? Because of the same picture. So it's somewhat confusing actually to relate gravity and entropy. Let me see. Yeah, so he says that the lowness in the sun's entropy, and by that lowness he means considerable remoteness from thermal equilibrium, comes from a huge reservoir of low entropy that is potentially available in the uniformity of the gas from which the sun has gravitationally condensed. So yeah, it seems still tricky to me, but you can give it a thought on the next week. On the next week. So yeah, that's it for today. Any questions?
Cool.